Okay, welcome to part one of our lecture video series for Wednesday, April 19th, where we are going to begin with a warm-up that allows us to kind of review the concept of total internal energy in a chemical system. So let's start with a little refresher. So let's remind ourselves about what total internal energy is. So in chemistry, the total internal energy of some kind of chemical system, which I use capital U to indicate. I'm sorry for all of us physics and engineer folks. You typically see U as potential energy. In chemistry, we use U to indicate total internal energy. But let's remind ourselves about what this looks like. So the total internal energy of a chemical system, U, is equal to the sum of the heat in a system Q and work. So Q is heat, and I'm going to go ahead and shorten this to W, which is work. And let's remind ourselves about where this idea of like heat and work come from. So in a general physical sense, if we were to talk about total internal energy, that would be a sum of all possible energies in a system. Typically in like kind of classical Newtonian setups, that would be something like kinetic energy and potential energy. Here in a chemical system, we are looking at heat, which comes from some kind of movement, be it translational, vibrational, rotational, of molecules in the system. So you have to remind yourself that any kind of material, unless it's some solid, is always kind of inherently dynamic, meaning there's always going to be some degree of motion and twisting and twirling and vibrating and such that happens in our molecules in that particular substance. And this movement gets translated into thermal energy, which you can kind of envision for yourself right now at your desk. If you were to sit and rub your hands together, right? If you were to create motion between your hands, the force of friction between your hands would cause for that kinetic energy acting against friction to then be converted into thermal energy, right? So we have this idea that like movement, kinetic energy, and temperature are all inherently related. As you cool things down, those molecules slow down. This is why we start to see a phase change, which we'll talk about at the end of the year. Similarly, if you start to heat things up, increase the thermal energy, you're increasing the kinetic energy of those particles, and you tend to have a phase change like into a higher energy phase change like liquids or gases. But in general, when we talk about the heat in a chemical system, this comes from our movement of molecules. And again, thermal energy, this is something that we quantify or get or calculate or expressed even as some kind of temperature. Okay, so the first component, heat. So movement of molecules translated into thermal energy, which we relate via temperature. And we're going to look at how that relationship works later on in this lecture. Then we have the work component of our total internal energy for a chemical system. And when thinking about work, we're thinking about force that's applied over some distance. And typically in chemistry, when we're thinking about things that are applying some kind of push or pull, which is a force over some distance, we're looking at some fluid, often a gas, that is either compressing or expanding. So the work that we're going to look at is the result of the compression or expansion of a fluid, typically gas. A fluid is anything that flows. In a system, and as such, we kind of specialize or specify, what kind of work this is. We call this pressure volume work. Now, if we were talking about electrochemistry, we could also indicate chemical potential energy or electric potential into our total internal energy system. But here in Chem 210, when we're just looking at kind of a basic, simple chemical system, like say a chemical reaction or a sample of some kind of material, we're going to talk about the total internal energy found within that system according to this equation here, where total internal energy is the sum of heat and work. All right. So let's do an actual warm-up. Like, let's do an example and remind ourselves about kind of the sign convention that goes along with how the total internal energy of a system can change. So for example, let's do A. If the change in the total internal energy of some chemical system is negative, then what is happening between our chemical system and our surroundings? Okay. Anytime in thermochemistry, thermodynamics in Chem 220, thermodynamics in physics or engineering classes, you see a negative sign associated with energy, this means like outward or away from system. So I almost think of it as like kind of a half completed arrow. So like that negative, just by convention, we decided is going to mean outward. So let's think about what this means in this particular question. So let's say that I've got a closed chemical system. So here's my system. And let's say that I have some initial total internal energy that I could measure based on the total amount of heat and the total amount of pressure volume work that is done or that is happening inside the system. And then let's suppose that there's some kind of change and we have our system now at some new final potential energy. So let's look at what kind of change, delta, could result in our total internal energy of our system having this negative sign, and then talk about what that means. So if I'm going to calculate delta U of our system, then I can say that is the final energy of our system minus the initial energy of our system. And if this is going to be negative, let's think about the conditions under which that is true. So if I have a big final internal energy and a small initial internal energy, then this difference is not going to be negative. So the only way that my system can have a negative change in internal energy is if my initial amount of total internal energy is greater than my final amount of total internal energy. So I would say here I have a high amount of total internal energy, whereas here I now have a lower amount of total internal energy. So what is happening then to my system that is going from having a large amount of energy within it to a smaller amount of energy within it? The only way that this can happen is if some of our total internal energy of our system is transferred out into the surroundings. Where this transferred to language is associated with that negative sign. Okay, let's look at the inverse. So what if the change in the total internal energy of our system is positive? Then what is happening between our system and our surroundings? So a little diagram here. So I've got, again, my system that is at some initial total internal energy. It undergoes some kind of change, and then my system winds up at some new final total internal energy. So anytime you see then this positive side, this is when you think kind of inward or toward the system. I think of this like the positive sign kind of reminds me of, I don't know, positive, like a little hug. And if you're hugging someone, you're like drawing them inward toward you. Silly, but you do what you can to get through chem. So let's think about how our change in total internal energy, delta, so change in total internal energy of our system, which is always final minus initial, could be positive. Like, when is this true? So this is the opposite case of when the change in our total internal energy was negative. Here, we need to have a higher amount of internal energy in our system after the changes happened compared to what we initially had. That's the only way that this result can be positive, if this number, the final internal energy, is bigger than the initial internal energy. So to put that mathematically, the initial total internal energy has to be less than the final total internal energy. Now, what does this mean is going on between the system and surroundings? So the positive sign indicates to us that some internal energy from the surroundings is transferred to the system. So our system itself is gaining energy by taking some from the surroundings. And don't forget the first law of thermodynamics, which states that energy is neither created nor destroyed. It can only be transferred or transformed from one form to another, or from one body to another. So if we're looking at what's going on in the change in internal energy of our system and the change in internal energy of our surroundings, we know that ultimately the net amount of energy that's transferred between the system and surroundings has to be the same. It's just one thing is typically gaining that energy and the other is losing. So we might write that the loss of energy from our system is equal to the amount of energy gained by the surroundings. Or if you want to think about our second scenario, the amount of energy in our system that is gained comes from a loss of energy from the surroundings. So we see the transfer out of our system or the transfer to our system. But in the end, because these are equal and opposite, we can say that the total internal, like the change in energy itself, would be zero, right? Like that energy is just kind of being passed back and forth. It's not disappearing into nothingness. That's what the first law states. So here, transfer out of the system, and here, transfer to the system. So in our next video, we are going to look a little bit more at the components of how we calculate total internal energy. So we're going to talk a little bit more about heat and work and their relationship, especially in some kind of closed system. And then we are going to look at the equations that allow us to calculate work, specifically pressure volume work, and calculate heat based on some kind of temperature change for a material. And that'll wrap us up for the day. So I will see you in part 2 of our lecture series relating heat and work.